Okay. So, I guess we'll get going. So I don't have too many announcements because we last week, this is a work period. I said I would consider making the due date Monday if a bunch of people emailed me, and nobody emailed me, so it was due on Saturday. But I mean, I kind of figured that would happen because, like, on Wednesday, most of the people were like either handing it in or being like, "Yeah, it's done." So I didn't expect anyone to have any issues. So yeah, nothing to say about that. I'll work on grading it this week so you can see back. But I mean, everyone talking to me seemed to know what to do, so I think it's fine. But I do want to talk about it. I haven't posted it yet, but I'm hoping to tonight, which is famous Travis last words for it'll be posted tomorrow, because I actually get home at like 9:30 p.m. So I don't want to work at 9:30. But I do have the final project drafted up. So that's the one that's like, because we have one more group project that's due sort of at the end of the term. That's sort of like it encapsulates chapters 2, 3, and 4. And then there's the group project, which has no specific topic other than it's related to something we talked about, but it's not from any specific chapter. It's like 4 questions, and they're all programming, literally all of it. Nothing, I mean, you should do stuff on paper if it helps you, but it's all programming. One of the questions is write a base converter where you're given, the user enters one base, and then another base, and then a number, and you convert it. Another one is implement some matrix operations, which we haven't talked about matrices yet, but do a multiplication, addition, etc. And you have to do some error checking to make sure that they actually work. And another one, and this is the one that I'm encouraging you, when I post it, start now. Because if you don't, then I have no sympathy for you if you struggle with it. I am having you implement a binary search tree and all of the methods associated with it. So that includes insert, delete, the various lookups, searching, and that sort of thing. I have it laid out very nicely. So you haven't talked about unit testing yet, and that's not something you talk about until like next term anyway. But all you need from unit testing for me is you will type pip install PyTest, which good luck on Windows 11. But if you need help with installing Python modules, well, you guys install pandas, right?
No.
Okay. Yeah, I'm kind of predicting that PyTest will be the same. It's kind of annoying. I'll help you with it. But all you need to know about it is there's a file, and you'll run it, and that will tell you what your grade would be. Right? I'm giving you all the tests, so there's no mysteries on what I'm expecting you to do. Right? If you pass those tests, you get 100%. Asterisk. If you actually implemented code that does the thing, if you just implemented code to pass the test specifically, then I will give you 0. So like, I will check your code too. But like, just as I had lots of spacing and comments and stuff like that in my solution, but it was 350 lines of code. So none of that is like particularly, like when we say that much code, that's not like, oh my God, there's so much I have to think about. No, like some of that is just rote stuff, right? Like you got some loops that take like 10 lines of code, right? But they're trivial, right? They're not hard to understand. And then there's like the function definitions and stuff like that, and all my comments and yada yada. It's probably like 100 lines of code. But it's conceptually not super easy to do binary search tree deletion. So again, I'm warning you to start on it now and work together as a group. And we're going to have a work period again at the end of the term. So you can ask me questions about it and I'll help you with it and that sort of thing. But it's very related to what we talked about, because we talked about binary trees, binary search trees, that sort of thing. And I just thought, hey, that sounds fun, right? It's challenging. So I've asked previous cohorts. I was like, do you think you could do this? And they were like, sounds challenging, but really fun. I would love to have done that. So the feedback is already good from previous people who don't have to do the work. So I guess you might end up hating it when you actually have to do the work. But I mean, it's programming, right? Most people will find it fun. But it is conceptually harder. You'll have to actually figure out how to implement things. And I want you to implement it in a very specific way. So like you can Google it and find out how people do that, but that doesn't necessarily imply to how I want you to implement it, because that's the business world, right? That's the real world. If someone says, implement this thing, and you just go to ChatGPT or Google and pull up the first result and copy and paste it, it probably doesn't work, and it's a disaster. So like you actually have to think about the problem a little bit. And I might have you write some description of stuff about it. So anyway, I just wanted to mention that that should be posted within the next day. And it's something you want to at least take a look at. I'm just covering my bases. I don't want people to be like, holy shit, Travis, that assignment was really hard and I wasn't prepared. Well, I told you that it is maybe hard. But related, but not related, we're going to talk about some stuff that's basically reviewed today and this week. So we're going to start talking about probability, which is all stuff that whether you took 30-1 or 30-2, they cover for what feels like an eternity in high school. And we're just going to do a review so that we'll make sure that everyone's on the same page. So announcements. No, I didn't write anything. None. Or see video or whatever. So we're going to start talking about probability, which involves a lot of terminology. I mean, that's just kind of math in general. It involves a lot of terminology. But none of this should be super unfamiliar. So we're going to start by talking about what probability really is, right? What is a probability? So we need some terminology. A random phenomenon is exactly what you would expect it to be. Phenomenon? Sure. Is a situation where we know the possible outcomes and we don't know which one will happen, right? There's just some outcomes and we don't know which happens. Where we know the outcomes, but not which one happens. And that's an important distinction for probability and statistics, right? We know what the possibilities are, right? We're not trying to analyze the unknowable or anything like that, right? We have a list of potential outcomes. So each observation of one of these is called a trial. Observation that's statistics terminology. It kind of matches up the science terminology for it, though. You do something and see what happens, right? That's really what we're doing here. If we record the result, that's called the outcome. Result, we call that an outcome. So when it comes to analyzing probability and statistics, that's really what we're interested in, right? Not just an outcome, but a collection of outcomes. An event is a collection of these outcomes. And it turns out that, that terminology, collection of these outcomes matches terminology that we've used previously. A lot of probability statistics does kind of boil down to set theory. When we're talking about probability spaces and event spaces, that's just a set, right? So the set of outcomes, right, is what we're interested in. So assume that we actually do something like this, right? We do one of these trials and we get some outcomes and we write them down and figure out what happens. So assume we do a trial. And there are n possible outcomes. So think, if you roll a 6-sided die, how many outcomes are there? 6. If you flip a coin, how many outcomes are there? 2, right? Heads or tails? Really. If it lands on its side, we would call that a failed trial. We would do it again, right? We wouldn't count it. We wouldn't record it. For our purposes, we're going to assume that all of them are equally likely, because then we have to start talking about sample distributions and stuff like that, and we're not concerned about that. So let's assume all outcomes are equally likely. equally likely. Now, if our event let's call it E for event, if that consists of M different desirable outcomes of M different desirable outcomes, then the probability of E happening is, I mean, it's probably what you expect. Probability, can't write. Probability of E is M over N, right? So I've used some specific terminology here. Normally what you would, the terminology you would use here instead of different desirable outcomes is different is successes in the trial, number of different successes. But I chose this terminology because success doesn't always mean positive, right? If a success in terms of your trial might be that the thing failed, right? That could be what you're trying to observe, and you would count that as a success towards your events for your probability. So that's why I call it desirable outcomes, because that's what you want to observe rather than it being strictly a positive thing. But it's essentially, how many things did I want to observe over how many total possible there are, right? That's the probability. That's the chance of that event happening. So again, like I said at the start of this, none of this is going to be, or it shouldn't be new. This should all be stuff that you've seen, but we're going to do some, a simulation and some just extra fun stuff on top of here. So as an example, suppose you roll a fair six-sided die. And when we say fair, that just means it's not weighted to produce, they're all equally likely, right? It's not weighted to produce a different outcome than another. So what is the probability of, so rolling a 3 as an example, rolling an even number, or how about not rolling a 3 or 5, right? And these are relatively easy to compute. So just to sort of explain what happens when we talk about probability and stuff, our set of possible outcomes really is the things we could roll on the die. Right? We can get 1, 2, 3, 4, 5, or 6, right? So N here, possible outcomes, is 6. So now we just have to think desirable outcomes. Well, we can kind of do these in our head. They're not particularly complicated. So chance of rolling a 3. So, well, how many ways are there to get a 3? Yeah, right. So it's 1 out of 6. How many ways are there to get an even number? 3. Yep. 2, 4, or 6. So it's 3 over 6, or 1/2, right? Half of the numbers are even, half of them are odd. The probability of not rolling a 3 or a 5, well, that would be a 1, 2, 4, or 6. 4 out of 6, right? So again, the probability here is nothing fancy. But there are some things I wanted to talk about probability because it's funny to say that, probability is a very simple concept, right? It's just number of desirable outcomes over total number of possibilities. And human beings are terrible at this. We're absolutely dreadful at probability, and we have a lot of superstitions and misconceptions about probability. A lot of them kind of stem from what it really means. So probability of something is sort of an expected, we call it an expected value sometimes when we're talking about, if I were to perform this event right now, what can I expect to have happen, right? So this is saying, hey, if I rolled infinity dice, 1/6 of them would be a 3. But notice how I said infinity dice. That's what this number means. It does not mean that if I roll one die 6 times, I will have seen 3 once. That's not at all what it means, even remotely. So this only applies when we're talking about extremely large amounts of trials. So we're talking like, well, if you wanted to roll a die to get the distribution of it, even 1,000 will show some fuzziness, right? So, I mean, imagine sitting there and rolling a die 1,000 times and recording it. You would probably see that, like, well, this isn't exactly 1/6, right? It's like plus or minus a little bit because of random error, right? It just happens. But if you did it like 1,000,000 times, you would probably see that that difference is very, very small, right? They're very close to each other. If they're not, then you would say this is probably not true, right? Something's wrong with the die. Because if it's fair, it should be equally likely all across the board, right? So that's one thing to note about is in order for us to actually see this probability happening, we have to do it a lot of times, right? A lot of different trials. And it's actually a name for it. It's called the law of large numbers. That when you perform a trial a bunch of times, and there's a formula to figure out exactly what is the large number for that. So a note of that is there's a lot of fallacies related to this. Like one of them would be the gambler's fallacy of, just the next one. I'm going to win the next one, right? That sort of stems from a misconception that you are owed something when it comes to probability. But no, you aren't. If I roll a die and, I'm sitting there like, wow, I haven't rolled a 3 in a really long time. Surely I'll get a 3 now. No. Because rolling a die, each roll is independent of the previous ones. The die does not know what happened previously. You just observed something interesting. That's all that happened, right? It has nothing to do with it. So you are not owed a specific probability ever. It's also a sunk cost fallacy of sitting there and going, well, no, surely if I keep at this, it will get better because I've already gone so far that it would be pointless to quit now. No. You could quit any time, right? At any point. But that also means probability is a bit weird because, okay, stupid question, but I'm going to phrase it this way. Who here plays video games? Okay, well, how many times have you sat there and you looked at something and it was like, this has a 98% chance of success, and you fail it 3 times in a row, right? Well, too bad. That happens, right? You're a statistic. It's not necessary that the random number generation or the probability is broken, right? That just happens. If you grab 100 people, on average, a random sample of 100 people, 2 of them have failed it, right? That's just what that means. So it's not impossible. And conversely, if something has a very low chance of happening, and phrasing it this way in terms of medical trauma is maybe bad, but we all have had experiences probably of someone we know suffering a horrible medical disaster that is a very low chance of happening, right? Like, it's like, oh, you have, only 1% of people have that happen to them. Well, get 100 people in a room and it happened to one of them on average, right? So, it's that's the stuff we're bad about with probability, right? It's not actually computing these numbers. It's the sort of psychology and understanding of probability and really realizing that it's just numbers and statistics. If you want to claim that something uncouth is going on in the background, there is a way to do that. It takes work. You have to run a bunch of trials. You have to run a bunch of samples. Totally random thing. For like a streaming website for artists, a bunch of people in a friend's stream were like, the raffle system is biased, right? It picks people disproportionately who've won before. And I was like, no, I don't think that's true. And then I actually ran an experiment where I did 100 trials, and no, it was not biased. What you're noticing is the people who are winning are the ones who come all the time. So it just seems biased because the same people are winning all the time because they're always there. So like, that's an example of people misinterpreting probabilities, right? They're like, well, you know, it says I have a 1 in 20 chance of winning, but the same 3 people are always winning. Yeah, because you don't know that the 19 other people are always different, except that one guy who's always there, right? So yeah, of course, shows up all the time.
It's just a trick for not someone to put another $20 in that slot.
But yeah, basically. And I'm not going to go into like the way gambling manipulates you into doing that. But it is basically preying on how bad we are at probability, right? Just not understanding how low odds really are. So just some remarks, not the philosophical kind or the psychological kind, just like about probability. For any event, the probability of it occurring is between 0 and 1. Occurring is between 0 and 1 inclusive. So that means it can be 0, it can be 1, right? Like the probability of me jumping and ending up on the moon right now is 0. Right? It's not going to happen. Same thing, the probability of me being in this room right now is 1, right? Like I'm here. So it can be 0 and 1, and going back to what I was saying, 0 is not the same thing as really close to 0. 1 is not the same thing as really close to 1. 0 is mean it can never, ever, ever happen. 1 is it happens literally every single time no matter what. So 0.0001 is, yeah, that can happen. It's unlikely, but it can happen. In addition, if you consider all of the possible events that could happen, the probability has to add up to 1. So the set of all possible outcomes has probability 1. So what that's essentially saying is that, you know, I have a die, it can roll 1 of 6 faces. When I roll the die, one of these faces comes up, right? Again, you could have a die that lands on its corner or something like that, but in terms of probability, we would count that as a failed trial and we would just run it again, right? Yeah?
So could you have something with the probability of 0 happening, like it never happens, so the probability of that never happening is 1?
Not in terms of the definitions of probability. So we could have events that could happen, but if, right now we're considering all of the possible outcomes. So we could have some specific outcome that has a 0 probability of happening, but then that means all of the other outcomes would total up to 1. And that usually comes up not specifically in your trial. Like you're not going to have 0 probability of rolling a 1. It would more be like I roll. It's hard to think of one off the top of my head, but when we're talking about intersections of events, right? So this has to happen and this has to happen, but they're mutually exclusive. They both can't possibly happen at once. So an example would be, we have a probability of Travis being in this room right now, and we have a probability of Travis being in another room. What's the probability of Travis being in both rooms at the same time? 0. I can't. Even though I have a probability of being here and a probability of being there, I can't be in both at once. So those are the situations where we'll have use 0 probability usually, because if it's strictly 0 in our event space, then we just wouldn't add it. So it comes up in those situations. And similarly for 1, that's more like, you know, I'm either in this room or in that room. I'm in one of them, so the probability of me being in one of them is 1, right? I'm in one of them. So if going back to the die, each face is 1/6 probability. So that means it's 1/6 plus 1/6, add them all up, plus 1/6 plus 1/6 plus 1/6 is 1. And this holds true for even more complicated probability situations, like when we're talking about distributions. If you remember in high school, you had like your Z table and you went into it and you looked stuff up. That also has a probability that adds up to 1, right? Even though it's a little more complicated looking. So this is kind of a general rule for probability and statistics in general. And sort of related to what I was rambling about before, it's important to note that in this discussion of probability, we did specify that we didn't specifically, but we'll usually specify that they're independent events. So what that means is the previous event does not influence the current event. So if I rolled a 1 on a die, I don't remove the possibility of rolling a 1 again, right? I could just do it again. So a dependent event would be I rolled a 1, and so now this happens. Or if I rolled a 2, something different happens. Those are dependent events, right? They depend on each other. Let's see. So more definitions. And this is kind of specific to one result that we really want. Since our events are just sets, we can perform set operations on them. So union, intersection, but specifically the one we want is complement. So if A, I don't want to say this. If A is some event, so it's just some list of outcomes, right? Some things that could happen. Then a complement is all events not in A. And so everything that's not in A. So when we talk about not rolling a 3 or a 5, that would be the complement is 1, 2, 4, and 6, right? Stuff that's not in A.
And that is every element in the set of properties, the set of possibilities that is not.
Yes, yeah. So you do have to have some sort of overarching set that you would be looking at to talk about the complement.
In
Yeah.
that case, the universe, which is the set of probabilities.
Yes. The set of probabilities for the thing we were talking about. So rolling a die, flipping a coin, whatever. So we care about this for one important property. I don't know if it has a name, but if we want to know the probability of an event not occurring, that is 1 minus the probability of the event occurring. So this is very, very helpful for an example is repeated failures or something. So an example would be this has a 5% chance of success. That means it has a 95% chance of failure. So often you'll ask yourself, okay, I performed this trial 5 times. What are the actual odds of me having failed? Because I did. And you just want to know, this sucks, right? That's super unlikely, but how unlikely is it? Then you can use this formula to very easily compute that, right? Because it would be, 0.05 to the power 5, and then that tells you the chances of getting that many failures in a row, and that informs you on how likely it is. But this formula is useful all across statistics. It's used very commonly. So it's just powerful to know. Specific, actually, I'll write it here. Just put that in words. Sometimes it's easier to determine when an event didn't happen versus when it happened. Sometimes it's easier to determine the probability of an event not occurring. Right, because from this formula we can just flip it around, right? This also says that the probability of A happening is 1 minus the probability of its complement. Right? That's just move this over and move that over and you get that formula, right? So if you're looking at an event that's kind of hard to analyze, maybe its complement is easier to deal with. Okay, so another experiment. Let's roll 2 dice. So suppose we roll 2 dice. Right, I'll say 6-sided dice, actually. And specifically, we're interested in the sum of those 2 numbers. So, you roll a 2 and a 3, the sum is 5, right? We're interested in that. So what is the probability of that sum being 5? What about it being bigger than 2? So, generally speaking, when we're talking about probabilities, we want to understand the probability space. So in this case, it's not necessarily that we're interested in the faces themselves. We're interested in the sums of those faces. But there also are a lot of different ways to make those sums. An example, we can get a sum of 3 from 1 and 2 or 2 and 1, right? We roll 2 different dice. So those are technically different outcomes, right? If we identify a die 1 and a die 2, each of those can happen. So we need to consider that when we're talking about the probabilities, because in a sense, that is twice as likely if we just treat them as being distinct. So first, let's determine our sample space. So I'm going to sort of collect it in a table. So we have a bunch of different sums that are possible, right? We can't get a sum of 1 because we roll 2 dice and 0 isn't a base. So we start at 2. And we can roll 6 and 6, which is 12. So we can get 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 as our total sums. So what we're really interested in is the number of ways we could do each of these. So this first one, 2, is easy. There's only one way to do it, right? Roll snake eyes. So I'm saying this is die number 1, comma, die number 2. Okay, that's the only way to do that. So for 3, you can roll a 2 and a 1, or you can roll a 1 and a 2. So there's 2 ways to do that. What about 4? Well, you could roll 2 and 2, or 1 and 3, or 3 and 1. So there's 3 ways to do that. What about 5? That's the one we're interested in, right? what is the chance of our sum being 5? Well, 1, 4, 2, 3, 3, 2, and 4, 1. So 4 different ways. Okay, but we also, so that means the probability of 5 is 4 over something, right? I mean, you can probably guess what the possible outcomes here is, because we're rolling 2 dice. Each of those can have one of 6 faces. So you multiply those together and you get 36. So we're expecting that this would be 36, but let's just keep going and counting all these to make sure that's the case. So how many ways can we get 6? 3, 3. We can do 2, 4. It's a 4, 2. This would be 5, 1, 1, 5. So 6 different ways, or 1, 2, 3, 4, 5 different ways. And then we're sort of noticing a pattern here. For 7, there's lots of different ways. It's a 1, 6, 6, 1, 5, 2, 2, 5, 3, 4, and 4, 3. These are all the possible ways to get it. This is terrible. I really beefed that. 6. And then now if we actually continue, we sort of end up going the opposite way, right? How many ways can we get 8? 3 and 5, 5 and 3, 6 and 2, 2 and 6. That's 4 and 4. Yes, thank you. So that's 5. And then this is going to be 4, 3, 2, and 1. Right? There's only one way to get 12, 6 and 6. So we sort of have this pattern here, but 1, 3, 6, 10, 15, 21, 26, 30, 33, 35, 36. So there's 36 outcomes. So the probability of rolling a 5 is 4 out of 36. But what about bigger than 2? So that would be basically all of these, right? Because here's a 2 bigger than 2. So probability of bigger than 2 is going to be 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 all over 36, which ends up being 35 over 36. There's only one way to roll 2, but this kind of indicates that formula I was talking about. Yeah.
Is bigger than 2? Is it bigger than 2 or bigger or equal to 2?
Generally, when we say bigger than, we would mean non-inclusive. So we would say bigger than or equal to if we wanted to include 2.
Would that be 33 over 36?
Well, bigger than 2 includes 3, right?
Oh, I know.
Yeah. So what we can actually do is we could say the probability of being bigger than 2 is 1 minus the probability of being less than or equal to 2. Right? That's sort of the complement of that, right? Well, this is pretty easy to calculate. Less than or equal to 2, there's only one way. 1 out of 36. So 35 out of 36. The same answer. Right, so this is kind of what I mean. This is a very mundane example where evaluating this directly, we had to add up all these cases and we had to think about them. But if we had started with this question and just said, okay, well, if I want to know the probability of getting anything bigger than 2, all I need to know is what is the probability of getting a sum of 2, 1 out of 36, and I just take 1 minus that. I don't care what the other outcomes are. I just know that that's the only one I don't have, right? So this could just be very, very helpful for saving a lot of time on computation. Okay, but if we have complement, that means we've got the other set operations too. So the other set operations apply to probabilities. I don't know why this is so squeaky. This is a new whiteboard, I guess. To events. So the union of two events exactly what you'd expect. So this is the event where A or B occurred. Where A or B or both occurred. And intersection is when both of them occur. So again, nothing too fancy there. So for example, if A is roll less than 4 and B is roll an even number, then we can pretty easily figure out these situations. And this is pretty common for probability and statistics, right? Your event spaces are worded in words, right? They're not a formula, generally speaking. It would be, hey, this happened. And it's your job to figure out what that means in terms of my event space. Okay, so roll less than 4. That means A, 1, 2, or 3. B is an even number, so 2, 4, and 6. So A union B is just the set operation now, right? It's 1, 2, 3, 4, 6. And A intersect B is 2. It's the only even number that's less than 4, strictly less than 4. So there are actually some probability and statistics terms that have to do with these intersections and unions. So the events A and B are called disjoint for the set theory word, or mutually exclusive for the probability word if A intersect B is the empty set. There's nothing in there. So mutually exclusive means they can't both happen, right? One or the other happens. It's not possible for both to happen simultaneously. And that kind of makes sense here, right? If we think of the intersection is when both of them occur, if we say this is empty, then that means there is nothing they have in common, right? They don't both happen simultaneously, so mutually exclusive. So if you have two disjoint or mutually exclusive events, I can't spell today. I didn't have enough coffee. So if you have two disjoint or mutually exclusive events, you can actually compute some probabilities pretty nicely. The probability of one or the other occurring is the sum. So this is probably, I really can't spell. This is probably one of the worst understand properties of probability, along with the multiplicative property. And it goes back to saying, if you roll a die 6 times, you're not guaranteed to see every face. That's not how it works. Intuitively, we understand that. But people will still think that, they're selecting, 20 people at random and there's 20 people and the same person can be selected, so that means of course I will be selected. No, because the same person can be selected 20 times, right? But if they are mutually exclusive, then that is true. So the flip side to that would be there's 20 people to select and you can't have repeats. That means being selected, like person A and person B being selected are not the same events, right? They're distinct. That means that we can just add up the probabilities. So probability of A or B, which is the probability of A union B, is the probability of A plus the probability of B. Now again, I'm warning, mutually exclusive. They have to be mutually exclusive events. Otherwise, there's some fuzziness. If they are not mutually exclusive, then, well, we have to actually fudge it. The probability of A union B is the probability of A plus the probability of B minus the fudge factor. It's minus the thing they have in common, right? So you have to take away all of the events that they actually share, and now we can add them up. So this is the part that's usually missed. So we can sort of think about this in terms of Venn diagrams, actually. So if we think about this, you know, you've got event A and event B. And I'm just going to shade it differently. So event A is all this stuff, and I'm shading it like that. So that includes that intersection, right? Yeah.
I just had a thought. How would you check for mutual exclusivity among multiple events? Because event A and event B being mutually exclusive does not imply that event B and event C are mutually exclusive.
So when we're talking about that, we would actually probably define it as A intersect B intersect C is the empty set, because we would want. So there would probably be two definitions here, and I think there are. I just don't remember the terminology. We would have this as a concept, but then we would also have A intersect B is empty, A intersect C has to be empty, and B intersect C also has to be empty, which would imply this definition, because if these are all empty, then that has to be empty, but they don't. The other one doesn't go the same way, right? And you can, again, think of it in terms of Venn diagrams. This is just sort of like the middle tiny piece of all three overlapping, whereas this would be all of the other overlaps, which includes that middle piece, right? I would say this is the stronger definition, and that's probably the one we would want to go with when we're talking about the same thing for multiple different events. But when we start analyzing multiple different events in probability and statistics, it gets way more complicated already, just by the nature of things. So I wouldn't worry too much about it. So I'm going to hatch this the other way. So we've got A shaded in this direction, and we've got B shaded in this direction. Notice how the intersection here has been shaded in twice, right? So if we take away one of those shadings, so we only end up with this, now we have the proper probability. Right? We're only including this intersection part once by subtracting it away once. And then going to the question of, well, how do we do this for multiple things? It gets a lot more complicated because you have to subtract stuff and then you have to add stuff back in. It's weird. But the point is, you can kind of pictorially see why when they're not mutually exclusive, we do this. If they were mutually exclusive, then they would look like this. Right, we've got A here, and then we've got B here. There's no overlap, so there's nothing to do, right? You could also always use this formula because the probability of the empty set happening, of like nothing happening, is 0, right? Because you did something, so something had to have happened. So this probability would always be 0 in a mutually exclusive event, right? So that formula will always work. So you could just also use that as a general formula. Okay, so there is something What time is it actually? Oh, hey, I've got a clock again. Awesome. So there is one other type of probability that is uncomfortable, and it's conditional probability. So the probability of B happening given that event A happened is called conditional probability. And it comes up all the time. So you can think like, what is the probability of me making it to class on time if my bus was late? Right? That's a conditional probability because it depends on whether or not my bus was late. Right? The answer depends on that. But that's, I would say, probably one of the more common types of probability questions is dealing with that sort of conditional probability. So we denote this as the probability of B slash A, and we read this as B given A, right? We even say that in the definition, right? Probability of B happening given that event A happened. So B given A. Probability of B given A. So there is actually a formula for this, thankfully. And it's a relatively easy formula, and it leads to a theorem that makes my life miserable, called Bayes' theorem. But we're not going to worry about that. So the probability of A given, or B given A, is the probability of A intersect B over the probability of B. Or sorry, probability of A. I have it mixed up. So why is this the correct formula? Well, let's just think about it. So we're saying we're interested in the probability of B happening given that some prior event did happen. So what we're saying here is we're saying, well, if this given event happened and we depend on it, then let's restrict our attention only to the outcomes in A. It did happen, right? So what is the probability of B happening out of the outcomes in A, right? And this is explicitly selecting the things that are in A and B, so this probability will make sense. We're not going to get a bunch of extra stuff that's not in A, right? So this is probably best seen in terms of an example. Suppose the following table has the counts of Canadians. This is something I pulled out of a statistics textbook, so I always have to read it. Has the counts of Canadians visiting Stonehenge. I really had to reach for this example. By their language preference, and region of residence, which is also very funny, because you can probably, if a statistics textbook is breaking up regions of Canada, there's like 4 of them, and 2 of them are an entire province each. I didn't make the example. Blame the statistics textbook. When it comes to examples in statistics, I really try not to just invent my own examples because it feels uncouth to invent fake statistics. So anyway, here's the table. So their language of preference is on top. And then we also have a total of all of the people surveyed who selected that language. And then we have the regions. Atlantic. I guess they probably constructed this specifically to demonstrate conditional probability more than anything. Quebec, Ontario, and then the rest of Canada. And then we all have totals down here. And then there's just numbers that go in here. So remember, these represent people who live in that region and selected that as the language of preference. And as I write these numbers down, I understand why they chose this example. 24, 55, 93, 76, and 248. So there are 248 people surveyed who visited Stonehenge who said, here's where I live in Canada on that list, and here's the language I prefer to use. So when we're talking about conditional probability, it makes sense that if you were to ask this question to a random person, their answer will depend on where they came from, right? Where they live in Canada. It makes sense, right? If the probability of someone from Quebec saying French is their preferred language is way higher than someone from Alberta, right? That makes sense. It makes sense that that probability depends on the event. What is the area you're from? So we can actually compute some of these statistics. So what is the probability? Probability that a random individual speaks French. So, okay, we go to our probability formula, it's regular probability. The number of people who speak French, 69 of them, over the total number of people surveyed, 248. Right, that's the probability of a randomly selected. You go to Stonehenge if this survey is to be believed, and you say, hey, are you from Canada? And the person's like, yeah. This is the probability of them saying their language of choice is French. So what is the probability? I'm going to start using shorthand here. French and from the Atlantic. Okay, well, so French is here. We're also saying they have to be from the Atlantic. So that's that specific number right there, right? But there are still 248 people to choose from. So this is the chance that someone is both of those things. Okay, what about probability that someone is from Quebec? Same thing. We look at it and say, okay, so there are 55 people from there. And there are 248 choices. Okay. But conditional probability, what is the probability that someone prefers French given that they're from Quebec? So this is what I was saying, where we're sort of restricting our event space, right? Because now, when we think about it, we're asking the probability of someone who chose French, given that they're from Quebec. So that means we already know that that is the answer to that question. We know that we're only asking about people who are from Quebec. So what is the chance that they chose French as their language? So two ways to think about this. We can just use the formula, which is the probability of French and Quebec. French and Quebec. So that's 50. And then chance of being from Quebec. Oh, sorry, I should do it like this. It's 50 over 248. Right, this is the probability of being French and Quebec. Right, 50 over 248. Then it's over the probability of being from Quebec. So that we just found 55 over 248. And then this is a fraction that we can simplify. It's 50 over 55. Right? These denominators go away. But we could also have read that from the table, right? We're saying, okay, we're interested in people who are from Quebec. So that's only this row here. We do not care about any of the other rows. So now our total is the 55. And we say, okay, well, what's the chance that someone speaks French out of 55? 50 out of 55, right? And this is why conditional probability matters, right? Because we look at this. Obviously, this answer is going to be really high, right? You pick someone random from Quebec and said, hey, is French your preferred language? They're going to be like, yeah, or whatever that is in French. So it makes sense that that's smaller than if we did the same thing for saying, okay, well, what's the chance someone from the West picked it? So that would be 6 over 76, right? Of people west of Ontario chose French as their preferred language. So it kind of makes sense why we would care about conditional probability, right? Any questions so far? Generally, like this is all stuff that has probably been talked about before. Everyone looks super enthused at 5:30 at night, but so I can make lots of topics very exciting. The basics of probability is hard to make exciting. It just kind of is what it is. But if you have any sort of passing interest in AI technologies, you need to know a lot of stats and probability. It's just the nature of it. If you were curious, hey Travis, why are you talking about probability? Well, one, there's misconceptions that I want to dispel. Two, it's just good to know probability, just for life. Just sitting there, how likely is that to happen? Well, am I getting screwed or not? But also the emergence of AI technologies, you're going to need to know probability and statistics probably eventually. It's just unavoidable. So just talking about it and getting you thinking about it is fine. Okay, so we're just going to do some examples. Yeah, okay. So suppose you have a bag of candies. It was just Halloween. That's pretty nice. Three of which are gummy worms. Then we have 4 licorice. Okay, so 3 gummy worms, 4 licorice. Suppose we take them without replacement, because you're going to eat them. Oh my God. So you don't put them back. That's what. So with replacement means you grab something, put it back. Without replacement means you grab it and don't put it back. So what is the probability of the first candy being licorice and the second is gummy worm? So you kind of have to think about what's happening here, right? We're going to reach in to this bag of candy here, and there's 3 gummy worms and 4 licorices, right? So there's essentially 2 sort of branching paths here. Either we grabbed a gummy worm or we grabbed a licorice, right? But we only care about one of them, right? Because we're saying, what's the probability of the first candy being a licorice? Okay, so this is the one we're interested in. So we grabbed one of the 4 out of 7, right? That was our chance of this happening. So what's left in this bag? That. Same thing again, right? We either grab gummy worm or licorice. So what's the chance of grabbing a gummy worm? 3 out of 6. So we are actually doing these events in succession, right? We're doing one, and then immediately after, we are doing the other one. Now, these are actually dependent events now. So we don't add these probabilities because it's more complicated than that, right? We do this one, and then, if we had grabbed a gummy worm first, then there would only be 2 to grab from here. So it actually changes the sample space, right? What we can grab from is different now. So we essentially follow along the set path here. We want to grab a licorice and then grab a gummy worm. And since we're doing both of those events in succession, and so that's the word we're looking for. We grab a licorice and then grab a gummy worm, multiply probabilities. So the probability here is 4/7 times 3/6. Right? Because we're going to do this event and we're also going to do this event. So when it comes to probability, a general rule is if the word is or, you probably add the probabilities. If the word is and, you're going to multiply the probabilities. We'll even write that down. And we even saw that with the rule, right? Where it was, if we wanted to, figure out the probability of a union, then we added them up with that little fudge factor if they were mutually exclusive. So probability or means add and means multiply. And this is not a hard and fast rule. It's not 100% accurate, but I would say it's 95% accurate. If someone, you would probably have to go out of your way to phrase a question to trip someone up with this, in which case you just are kind of an ass and constructed a question bad on purpose. So this right here, this and, there is a formula. For multiplying probabilities, A and B given A. I would say this formula is generally more complicated than it needs to be because if these 2 events are independent, where's the sheet? There it is. If these 2 events which these 2 are, because grabbing a licorice did not affect the number of gummies we could grab, then this rule simplifies. So PA and B becomes P of A times P of B. So again, this rule, just like with the union rule, there are conditions where it works out really nicely. And in fact, unlike the union rule, which required mutually exclusive events, which is not a guarantee at all, this one is talking about independent events, which if you read a statistics textbook, almost every single experiment you look at says, assume we're looking at independent events, right? We're looking at an independent random sample or something like that. So this word here comes up a lot. And being independent means that the probability of the event happening does not depend on the other event happening. Okay, well, I have one more example to do. But I want to do something fun in the last 5 minutes because talking about probability is exhausting. So what I want to do is actually talk about a fun little experiment, which will require me to hook up my laptop to the screen. So let's hope that works.